chair in mechanics, materials, and aerospace engineering at Illinois Institute of Technology. Before that, he spent some time at Florida State, where he was an endowed professor there. And previous to that, he was at the University of Florida. He received both his BS and his PhD from Penn State University with a master's at MIT in between. He's very well known in the active flow control and aeroacoustics community. He's done a lot of work in building actuators and actually implementing control methods in experiments, which is a very important step when we're thinking about flow control. People like me just do theory. People like Lou actually see if these things work. Okay, he's received funding from pretty much every source that funds these sorts of things, including NASA, the Air Force, ONR, NSF, Boeing, Lockheed Martin, GE, Gulfstream, among others. He's a fellow of AIAA, ASME, APS, and the Royal Aeronautics Society. And he's also an associate editor of Experiments in Fluids. So I'm very excited for our seminar today, and I'll pass the mic off to Lou.
Thank you, Aaron. And thank you, everybody, for coming. Appreciate it. It's been a really nice fall day here in Ann Arbor. Enjoyed it quite a bit. And before I get going here, let me start by acknowledging the person who really did the work here, and it's Eric Deem. This was his PhD, and Eric's now working for Lockheed Martin in the area of hypersonics. And I also would like to acknowledge my collaborators on this work, Rajat Mittal, a longtime collaborator from Johns Hopkins University, and Clancy Rowley from Princeton University. And then Maziar was actually also quite helpful. He was on Eric's PhD committee. So before I bounce into the talk here, I just want to show you where IIT is. So you're actually looking at a view of downtown Chicago in the background, and it's about 2 miles from south of downtown Chicago, so-called Magnificent Mile that you may all know and love. And IIT is located there close to where the White Sox play. And you can see the campus there is what's right before you. And this is actually a view from where the top administrators in the university sit in the tower looking over, and the arrows pointing there where mechanical materials and aerospace engineering is. So I'm going to talk today about some adaptive control of this very separated flow that you see in front of you. So I don't think I need to say a whole lot about the importance of separated flows in terms of the impact they can have on aerodynamic applications. This particular image is a high-speed PIV image that Eric took of his experiments. So the flat plate is the bottommost surface flow is from the left to the right. And if you look at this, it's something I'll harken back to as I go through the talk. You'll see the incoming, it's a laminar boundary layer coming in here, and you can see it lift off the surface. You can see this formation of these coherent structures in the shear layer, and then a reattachment further downstream on the aft portion of the plate. So the objective here will be, as you'll see, to place an actuator just upstream of separation. And we'll use an array of surface mounted pressure transducers underneath that separation bubble to essentially do a physics inspired but data enabled adaptive control system to attach this boundary layer. So a little bit of background on separated flows and their control. If you look at flow, for example, over an airfoil at a modest angle of attack and reasonable Reynolds numbers, you often see several characteristic frequencies in the time-dependent phenomenon that you measure. For example, you'll often see some shedding in the wake, characterized by its frequency. You'll see that shear layer that I just showed you and some characteristic frequency of those structures passing by. And then when the bubble reattaches, you can see a third frequency corresponding to this reattachment frequency. And we can normalize these into what's essentially a Struhl number, but in this community, it's often called F+, which is frequency times a length scale. So L-sep, for example, is the length, the nominal length of this separation bubble, which I'll refer to in here, and then normalized by the approach velocity. So in terms of control, there's a number of studies, some of which are illustrated here, that have identified this shear layer frequency as the most effective frequency for control. But then there are other studies that have come along and said, well, that depends on where you place the actuator. For example, the cross here indicates the location of the actuator. So if it's moved further upstream, they find that forcing at this lower frequency of the wake is more effective in this reattachment. And if you move it just a short distance further downstream, closer to where it separates, then the separation bubble frequency is more effective and somewhere in between. So there's this debate about what's really the best frequency. Is it a single frequency? Which led us to kindly say, why don't we try and do this using some feedback control approaches. So a little bit more detail on this. So this is actually a visualization of flow over a NACA airfoil at a modest angle of attack, where you get this leading edge stall. And one of my former PhD students studied a number of ways of attaching or reattaching this flow years ago. And he indeed tried a disturbance rejection controller, which, so there's actuators placed here and here, and he has an array of pressure transducers. So you'll see we've gone sort of in a circle here as I go through this. And he was using essentially system identification approaches to identify a model and then generalized predictive control to attach it. Now, what he found, which was interesting and illustrated here, is that the control would work. It would attach the flow. But in order to drive the disturbance, which was measured as essentially the magnitude of the pressure fluctuations down even more, it would turn the actuators off. If you've ever been in a lab that runs these synthetic jet actuators that are piezoceramic, they're extremely loud. They're in essence the buzzers that you have in your, the page function of your phones. So these themselves can generate pretty strong acoustic signals, which of course the pressure transducers don't know anything about. So when you're trying to drive the disturbance to zero, you've attenuated the separation. The only other thing you hear is the actuator signal, so it drives that down even for. And then this whole process sort of repeats. So fruitful, but not quite what we wanted. So what we're after is an active control approach that will mitigate that separation. And to be fair, there's a fair amount of literature out there, and I'll just highlight a couple cases that I think are kind of interesting. And so, for example, I mentioned Etienne's work. He also looked at some data-driven approaches. So this downhill simplex method is essentially an optimization that is a gradient descent algorithm. And he was measuring the lift and drag from a balance and using this to adjust the actuator signal. And this responded on the order of 1 hertz, so relatively slow. The work of Rees et al., years before neural nets have become the rage, was using a neural net to derive a model. And this was pretty intensive. It actually it worked, as you can see, from the uncontrolled to the controlled case, but it was very slow. It took a lot of training data to do this. And, but again, the potential advantage of this was that it was model free. If you compare this to, at the time, some 10 years ago or so, people were driven largely to look at reduced order models that use some form of a Galerkin projection approach. So for example, POD stands for proper orthogonal decomposition. I'm sure many of you in the room know this quite well. And so this is a physics-based model. And essentially you do this projection and you end up with a set of nonlinear ordinary differential equations. But then when you try and institute control, what happens is these modes deform. They're no longer, the basis functions are no longer appropriate for the control. So you have to adapt these. And many people indeed are working on variants of this as we go forward. But it can be some frustration. I'll show you a little bit of that Eric tried early on. So our overall goal here was to come up with an adaptive model that retains the essential physics, but now is fast enough to respond to the timescales in the flow and will, as I just said, adjust to the deformation of the base state as you turn on control, because the flow itself changes, and do so in an automated fashion. So now on to the experimental setup. So I was collaborating, as I said, with Rajat, who's a computational person, and we looked at a configuration that was popularized by Ney and Moyne. in a JFM paper, which we thought was quite interesting to try. And it's this elliptical flat plate. So it's elliptical leading edge with a flat plate. And you can see it has a square trailing edge. And basically, this is about 40 centimeters long, 3.8 centimeters thick. We place an actuator over the central 2/3 of the span of the model, just upstream of separation. And we have an array of electric mics, okay? So these are literally, you can buy these WM61As from Panasonic for about $1. That's how cheap they are. And they're just really hearing audio mics. And we use this to detect the pressure fluctuations. And the cord Reynolds number based on the overall 40 centimeter length is about 100,000 for most of these experiments. Okay, so how do we get the separation bubble on a flat plate? Well, we induce an adverse pressure gradient. And this is again the idea of Ney and Moyne, where they imposed a zero net mass flux suction and blowing at the domain boundary. In our case, it's in the wind tunnel ceiling. And so you siphon off and with a fan a portion of the flow and then re-inject it just downstream. And then you can move the duct and or the plate with respect to it and adjust the size of the separation bubble. You can make it a closed separation bubble, reattach on the surface, which is what we'll look at here, or you can move it far enough forward to where you actually get like a leading edge stall case where it connects to the wake and get some very complicated topologies. This was nice because Rajat was doing large eddy simulations and he could get to pretty high Reynolds numbers because his grid was very simple here, just a rectangular coordinate system. And he used the immersed boundary method, but I'm going to be focusing in on the experiments today. So the PIV, which we use extensively, comprises this separation region. And there's a second PIV region that is zoomed in on the actuator slot that you see here. And the reason for that is that enables us to measure the momentum, the input of the actuator, so we can evaluate the control authority. If you take a look at a flow visualization on this using PIV, where we've computed vorticity off the surface, you can see how the boundary layer lifts up off the surface, the formation of those structures, and the transition to a turbulent shear layer, and then reattachment. And then the time averaged circulation bubble, recirculation bubble is indicated by that dashed line. So you're going to see here that I'm going to characterize the length of the separation bubble. It's roughly 24% of the cord, and the nominal height of it, which is about just under 2% of the cord. And the shear layer, the frequency of this normalized to a Struhel number is about 2. So it corresponds to that shedding that I was telling you of the shear layer frequency. So here's the synthetic jet actuator. As I said, so it's about 61% cord just upstream of separation. And I'm assuming most people are familiar with this device. So it's essentially, if you cut away this, it's a cavity that has a long slit, and there's inside the cavity, there's 4 of these piezoceramic discs that are all operated in phase. So just think of it as a bicycle pump. Okay, when you push in, it ejects fluid. When you pull back, it pulls fluid in. And of course, it's doing this in some sort of oscillatory fashion. And obviously you don't have to, primary benefit of this is you don't have to pipe any high pressure air to this. This is zero net mass flux, okay, but it ingests momentum, a net momentum into the flow. So we use what's called a burst modulation waveform, and that's illustrated here. So in this case, you see there's a high frequency sine wave. We call that the carrier frequency. And that's at about 2 kilohertz, which is the resonant frequency of those actuators. That's how you get high output. But most of the frequencies that we're interested in controlling are actually much lower. They're on the order of 100 hertz or so. If you run the actuator at 100 hertz, it doesn't really produce any output. So a way to get around that is to use this so-called burst modulation, where essentially you turn it on for a period of time and then turn it off. And this period, from where it starts to where it repeats, is 1 over that modulation frequency. And that's the frequency that you really care about in terms of controlling the flow. So we're going to use the well-established momentum coefficient. as a dimensionless measurement of the input to the system, and the forcing frequency we'll call F plus will be that modulation frequency normalized into a Stroll number, as I've described before. So as with most of these things, what you typically do first is do a series of open loop experiments. I mean, open loop control experiments, where we're just changing if you will, the amplitude to the actuator and just scanning through a series of frequencies to see how does it respond. And there's two different C mu's that you can see here. And what we're showing in this plot is the height of the separation bubble normalized by the chord versus this dimensionless forcing frequency F plus. Now the nominal height is shown here as this dashed line. So control is effective if you stay below this line. You're reducing the height of the separation bubble. And you can see there's a rather broad range of frequencies around an F plus of 2, where this thing seems to respond quite nicely. And indeed, I showed two different snapshots of the flow, the baseline separated case, and then when we turn on the control for these different C mu's. And you can see how it basically is able to mostly, almost completely reattach the flow. Not quite, it's still somewhat separated, but this gives you a picture of what's going on. So we have an idea that the open loop control can work using this methodology, but this is a very painful process. It takes a long time to sweep through these cases and by trial and error and find what works. We want to do this in an automated fashion. That's really the overall objective. So how do we come up with a reduced order modeling approach that will do this? Eric looked at really three different cases. So one is the Galerkin projection, which I mentioned earlier. A second one is similar to that, but it uses dynamic mode decomposition, which I'll talk about here a little bit. And in both of these cases, we're essentially using a 20 POD modes, and the POD coefficients, the temporal coefficients of the POD modes become the states that we're trying to predict. And then finally, I'll show you what we ultimately settled on, which was that online DMD. And this uses 13 electret microphones and runs in real time. And when I say real time, the data system rate of this was about 10 kilohertz. That's how fast the data system was running. So we're acquiring this in a digital system. So I'll get to that in just a few minutes. So let me say a little bit about DMD for those of you unfamiliar with it. So it is a technique that was popularized by Peter Schmidt roughly a decade ago. And the basic idea is that if you have a discrete time system and you take x of k here as the current time and you map it with a linear operator matrix A to the next time step, x of k plus 1. So what is x? X is your data matrix. So literally your first snapshot of data is x1, your second one is x2. So you stack these along the columns, and then x of k plus 1, you notice, takes over at the second time step all the way up to the last one. So it's literally just moving it one time step ahead is what this linear operator is. So this is obtained through a least squares process, projection process, and you get the pseudo inverse. So this matrix A DMD is y times the pseudo inverse given by x plus, okay? So this gives you a high dimensional linear representation of a nonlinear system. And if you read Clancy Rowley's paper, it has ties to the Koopman analysis. Now, most people use DMD to get at the eigenvalues and the eigenvectors of these modes. So basically, you can think of it as a given frequency that will oscillate, a mode that's going to oscillate at some frequency. And you have a corresponding frequency of oscillation. We are actually interested in the A matrix because we want to implement this in a state space model for control, okay? And so we get the modes, and we also will typically look at some measure of the amplitude of these modal coefficients to get an idea of which one's the most important. So when Eric tried the second approach where we use the POD coefficients and we use DMD to map these things forward, this is pretty indicative of what happens in these processes. So I'm showing you the predictions for the first, second, and third mode measurements compared to the model. And you can see it starts off fine, but after not too far into the future, it starts to deviate. And this model in itself isn't sufficient. You need some corrective action to improve this. And so this is what led us to saying that maybe this could work if we would adapt this model. All right, and that was the basis for the online DMD. So that's going to lead me to this DMD process. And to illustrate some of the basic concepts that I want to talk about, if you look at sort of a phase space of your state space, you might have an oscillator model, and you get some linear model that matches maybe reasonably well to the data. And then when you turn on forcing, you're trying to often bring these states to zero. You're trying to bring the disturbances to zero. So bringing it to the origin of this. And so you have this evolution now to a new limit cycle. And this is going to then deform the basis functions, right? So you need this model to adapt as you turn on the control. And so we want to be able to cope with the nonlinearities that are present in some fashion. And we want to use this model to update the control law. The control law that we're going to use is the linear quadratic regulator that if you've taken a class on optimal control, you learn all about this. This is an optimal control that is based on an infinite horizon with white noise measurements, and you have access to all the states, which is what we do here. The key point, as you'll see, is that we're able to adjust the penalization function that compromises performance, trades off essentially performance versus how much oomph, if you will, that we're putting into the actuator. And I'll talk a little bit about that in a minute. So how does DMD work? And this is an illustration of this where we're going to use PIV as the data matrix here. So essentially think of it, we take measurement in a plane, we have two velocity components times the number of measurement stations. So that's about 20,000, okay? And we'll take 10,000 snapshots, use a reduced rank model in this case of 25, and see how this works using what's called total least squares DMD, which is a variant of DMD that's quite robust for measurement systems that have noise in the data matrices. And this is an excerpt of the response where we're showing the eigenvalues, and this is the unit circle. And it's hard to see, but basically everything's falling pretty close to the unit circle, which is what you would expect, because essentially you have a steady state oscillations. And they're not damped, so we don't expect them to be inside the unit circle, and they're not unstable, so we don't expect them to be outside the unit circle. So this is what happens. And if we look at the amplitude of these disturbances, okay, starting with different initial conditions, invariably the one that has the strongest amplitude is the mode that I'm showing here. And remember, this is the plate, and this, you recall the shape of the separation bubble. So this is clearly a shear layer type of instability or shear layer mode, okay? And I'm showing you this dimensionless vorticity at that characteristic frequency. So it's quite clear that the DMD is able to capture this. Now, this is what a movie of that looks like. Well, I thought I was going to be able to show you that. But basically this, if I played this, it would just propagate left to right, showing you essentially, as you might imagine, vortical structures moving through the shear layer across the plate. So you can't use, although some people have done this in some experiments, you really can't use PIV as a practical feedback control system. It's just not, it's both not practical and it's really not feasible when you have any significant bandwidth in the system. So we surmised that these vortices that are propagating in the shear layer should leave a footprint on the surface of the plate. You should be able to pick this up as like a wave-like phenomenon through those linear array of microphones that are underneath of it. And then that now 13 sensors instead of 20,000 sensors might be sufficient in order to get the physics of what we need for control. But before we did that, we wanted to make sure that there's consistent dynamics between vorticity that we measure with the PIV system through the velocity field and the pressure that you might extract in the flow field. So to do this, we essentially assume the flow is two-dimensional. we take the Navier-Stokes equations and take the divergence of it to produce so-called pressure Poisson equation. And we neglect the three-dimensional terms. And you notice it's essentially Laplace's equation where the source term on the right-hand side is computed. It's related to Q, if you're familiar with the Q criterion. And it's actually computed from the 2D PIV snapshots. So we solve this equation using a finite difference approach, and we use the boundary conditions that are described in Cattafesta and Van Althuizen in an experiments in fluids paper over this domain, essentially just above the separation zone. And this is what it looks like. So the top movie is showing you the vorticity. So you can see the shear layer lifting up off the surface. And the bottom one is showing you the CP fluctuations, okay, fluctuating pressure. And so you can qualitatively see high and low regions of pressure as these vertical structures move across the surface, which is what we sort of expected to see. And then we said, okay, this means that we should be able to capture a footprint of this pressure disturbance on the surface. To check this a little bit more quantitatively, yes, sir.
Boundary condition you have on the right, because
the boundary condition on the right is an unsteady X momentum equation, like the 1D X momentum equation for the outflow, similarly on the in. And essentially it's a normal pressure gradient, zero normal pressure gradient, like an Euler boundary condition on the bottom wall. And the upper one uses essentially a version of an unsteady Bernoulli equation.
it's impressive because you have strong vertical structures leaving and it's still able to pick it up.
It's able to pick it up because we were worried about these waves coming back and contaminating the surface. So that's what we're using. And if you just check for consistency, I've overlaid here the pressure contours on top of the vorticity at different times. And you can see the propagation of these structures. And these are consistent with our measurements of cross correlations underneath the surface and consistent with the peaks and valleys in the shear layer structures. So now we want to say, okay, can we do this with this online DMD process? So credit Clancy and his student Zhang on this. It's a pretty neat trick, I thought. So remember that this A DMD matrix is the Y data matrix, which is the shifted data matrix, times this pseudo inverse, okay? Now, if you look at the pseudo inverse, it is the transpose of the data matrix, and then this multiplies the inverse of the product of X times its transpose. Okay, great. Well, what we do is we define two variables. Q is the Y times the X transpose, and P is the inverse of the product of those two matrices. Okay, great. Why is this important? Well, because what happens is if you want to do this in real time, you're taking a new data measurement, which becomes X at K plus 1 and Y at K plus 1. And so now we can create augmented Q matrices and augmented P just at the next time step. So I've done that for Q, and you multiply this out, and you can see the new Q is the old one plus a simple multiplication with a transpose operation. And the new P, however, is a little more complicated. When you multiply this out, if you want to do this exactly, you have to compute an inverse of this matrix, okay, which is what we're trying to avoid for speed purposes. So instead, we take advantage of the Sherman-Morrison formula, which takes the inverse of this matrix and writes it as in a recursive formula where it's P plus some scalar, gamma, okay, times just a product of matrices. So this is very fast, and this enables us to then compute the updated DMD matrix on the fly. And as I said to you earlier, we're able to run this at 10,000 hertz, okay? So this is orders of magnitude faster than the dynamics of the system and update this DMD matrix. There's one last step or two last steps that I have to quantify. This is for what's called an autonomous system. There's no input here. Okay, you notice it's just essentially A equal AX, and you advance it, but we have to add in control. So in a state space model, we're adding in this B times U. Now remember, U is the prescribed input that we're going to use. It's going to be our signal that's going to modulate the actuator signal. Okay, it's going to adjust the amplitude of that. And here, what we did is just implemented the DMD with control that Proctor proposed some years ago. So essentially, we just take the same matrices we had before and we created augmented matrices. So A DMD gets B appended to it and X gets U appended to it. And it's exactly the same form as what I had on the previous slide, and everything else just applies. So now we can apply online DMD with control, just like I said before. Now, one last thing that I think was pretty important that we found is that we want the model to adjust rather quickly to the deformation in the base state. And if you think about it, what we're essentially doing is accounting for all this information over all time. So instead, we want to really weight what's happening now more than what happened a long time ago. So to do that, we introduced what's called a weighting factor, where the updated matrices get divided by this constant kappa, and it varies from 0 to 1, depending on how aggressively we want to attenuate prior information and really emphasize more recent history. So this gives us, in essence, a time varying but linear representation of this separated flow, which is inherently nonlinear. How well does it work? So this is a spectrogram, if you will, where we're plotting essentially frequency that we get from the online DMD. And from this, we can, using DMD, we can extract the frequency. And remember, there's only 13 sensors here. So there's a limited number of modes that we can get and a limited number of frequencies associated with these, and they occur in complex conjugate pairs. So the shear layer frequency settles in to the value that I was showing you earlier after roughly 10 to 15 shear layer cycles. So that shear layer cycle that I was showing, that frequency is about 100 hertz. So this means after about 0.1 seconds, this thing has, starting from a random initial condition, it's identified the system. Okay, which I think is exactly what we were after. And this is what that mode actually looks like if you plotted the real and imaginary parts of the DMD mode that you extract from this. Okay, which is consistent with that wave propagating across the surface. Okay, so now we want to use this LQR control. I'll have a few words to say about that. I'll show you how fast this system responds, and then I'll show you how robust it is to changing the flow conditions. We'll vary the Reynolds number. So let's start with the LQR control. So LQR control is a standard optimal control where you use what's called state feedback. So remember, the states are the coefficients that we're getting out of the DMD model, right? And so negative feedback, so you have some matrix K that multiplies that. That U is what you're going to use as your modulation signal for the actuators. When you use it in this form, this is your now updated state space model. A plus BU becomes A minus BK. And the matrix K is determined by minimizing this cost function. And you notice that the cost function has two parts. So really it's like X transpose X is like the power of the coefficients. So if you're trying to drive these to 0, that's essentially a measure of the power of the disturbance. And there is a weight matrix Q in here. And the second term is like the amplitude squared, U transpose U with another matrix that multiplies this, okay? The relative importance of the control input versus performance is the trade-off between these. So we can adjust, keep Q as essentially an identity matrix and adjust the magnitude of R up or down to see how much this changes overall performance. The optimal solution for K is given by this equation, which actually comes from solving the well-known discrete time algebraic Riccati equation given in the last line. Okay, so this is, if you take an optimal control class, you'll spend weeks of lectures going through the derivation of this and implementing it. So we implemented this in an NI real-time Veristan system. And as I told you, we run the primary control loop at 10 kilohertz, 10,000 hertz. This is over a factor 2 orders of magnitude above the shear layer frequency that I showed you earlier. We set Q to be essentially a scaled version of the identity matrix. And we're going to vary this weight matrix here for the penalty term on the actuator, and you'll see different values. So nominally 0.5. And we adjust the attenuation factor, that kappa that I showed you earlier, so that we get about 10% attenuation after 35 shear layer cycles. And it really wasn't too sensitive to this, other than we had to have some finite attenuation. We couldn't let it just be no attenuation. And so we turn this thing on. The baseline is the top plot. These are the time average flow fields showing you vorticity. And then the bottom plot shows you the reduced size of the separation bubble for this particular value of the penalty term on the actuator input. Okay, so to explore this a little bit further, by varying R, we can from 0.1 to 10, so over 2 orders of magnitude, we vary R. We get essentially a different size of the separation bubble versus the effort. And this is what's called a Pareto front. So essentially, this is like an optimization curve where you're trading off the relative importance of those 2 terms. All these open loop cases with the circles here are all the other cases we tried. And what you'll notice is that on the one hand, the closed loop control achieves the best that the open loop control can do. And as you'll see, it does it in a fraction of a second, okay? And if we allow greater C mu, more effort out of the actuator, we can ultimately essentially eliminate the separation bubble. If we restrict the actuator to not work very hard, then we have to live with a larger separation bubble, okay? And this is the trade-off that you have between the 2. So looking at this another way, again, here's this separation bubble height. And here's the corresponding effort, varying R from 0.1 to 10. And I'll highlight a couple key cases. So for example, if I choose this weight factor as 2, this results in a separation bubble height of 0.006 roughly, okay? And C mu of 1.3 times 10 to the minus 3. If you compare this to the open loop case, this is a 30% reduction in the amount of momentum to get the same separation bubble. Okay, so less effort than the open loop case. Alternatively, if we reduce R by a factor of 2 down to 1, now we can have a little bit higher C mu. The separation bubble height gets a little bit smaller. And for the same C mu, this is 16% smaller bubble height. So again, slightly outperforming the open loop case. So if you look at the signals themselves, I'm showing you a spectrogram where we plot, we record the U signal that's going to the actuator, and we perform essentially a spectrogram of that. And we do this for different values of this penalty from 0.1 all the way up to 1. And I would point your attention to how this behaves. At very low frequencies, at very low time, we turn it on, okay, it's concentrating on a Struhl number that's primarily, for all these cases, around 1.5. And what we see, though, later on is after control is firmly established and we just let it run, it's not running at any particular frequency. It's very broadband in nature. So I'm not sure exactly what the physics of this, we still don't understand this, but the idea is once the flow is attached, it's possible that it's just trying to keep the flow turbulent. I don't really know, but it's not locking on to a particular frequency anymore. It has to adjust, and it does so, and it produces essentially a broadband random input signal. So how fast does this work? So what Eric did is measure this with the time resolved PIV system, measured the separation bubble height, and did sort of a running average of this. And again, remember, this time is the actual physical time normalized by the shear layer frequency. So you can see that after about 10 to 15 shear layer cycles, it starts from a random initial condition and attaches the flow, or at least mitigates significantly the separation. This was working before, but this movie is not playing here. And it was just going to show you this window to give you a feeling of how this thing, shear layer, which is lifted up off the surface, essentially attaches or almost reattaches completely to the surface over that time scale. Finally, I just show you how robust is this to different flow conditions. So I can tell you from experience in the past, when you design a control system and you change the conditions, you'll very often have to go to a redesign. It's not a simple tweak. So this was very nice to see. We varied the Reynolds number down and then up. So you can see 0.9 times 10 to the 5 up to 1.25. You can see that there's a significant 20 to 30% change in the shear layer frequency. And you can see at lower Reynolds numbers, you can imagine it's got a larger separation bubble. And then you turn on the control and it's able to reattach the flow or significantly reduce the adaptive the size of the separation bubble. And then finally, I'll note that if you look at, not sure what this guy's doing, but if you look at the size of the separation bubble, again, this running average, you can see that all this is about the same time scale, 10 to 15 shear layer cycles. So really physical terms, that's about 1/10 of a second. So you turn it on, random initial conditions, and boom, it just snaps the flow right into place. And so that part of it was pretty nice to see, changing the Reynolds number. So I'll leave the conclusion slide up here and just mention some limitations of this and where we'd like to go with this and some challenges. So first of all, that was a laminar boundary layer. Turbulent boundary layers are obviously much more interesting. They're much more broadband. They're much more resistant to separation. And when they separate, the question is, will this same sort of approach apply to that? I think that's an interesting question to look at. We use the linear version of this, obviously DMD. There are extensions there are other reduced order modeling techniques, extensions to DMD for example, extended DMD and others that might be even better than the approach that we've used here. And we use a simple LQR where we were just solving the Riccati equation. We could probably conceive of a better controller with a finite horizon that could be more effective than what we've used to date. So these are, I think, some interesting areas for further exploration. And if you're interested in this, you can get the paper here. And I'm happy to stop here and answer any questions if you have any. Thank you.
Question.
So, yeah, very nice work. Okay. What is the order of the system, the size of A in the online DMD?
Well, it's a 13,
By 13.
yeah. So 13 by 13.
Really nice talk. I was trying to understand the online DMD from the pressure. So the modes correspond to 13 pressure locations at prominent frequencies. That's your state vector, is it? You're giving it.
Well, let me put it slightly differently. The states,
Yeah.
you have 13 measurements. Okay, so that's the size. So they become your data vectors, your X's and your Y's. So when you're essentially doing an eigen decomposition of this, the most you can get is 6 complex conjugates and then 1 real, because we have an odd number. And each one of these would correspond to a particular Struhl number frequency and have a shape associated with it. We can compute that post-processing. We don't do that on the fly. We just, because what we're trying to do is actually get the updated A matrix, which is really our best linear approximation of the state, and B, right? And use this to update the control signal to the actuator. And we're doing this every time we acquire a new data point, 10,000 times a second, there's a new column vector that gets inserted. So the online DMD just recursively uses the Sherman-Morrison formula to arrive at essentially your optimal ADMD without having to do a matrix inversion. Yes.
Early on, I think you mentioned that you had to work around the fact that the resonant frequency of your actuators was quite high. Is there a reason, or are there other actuators available that have like a smaller resonant frequency, like a different size piezo or something like that?
You're absolutely right. And this is actually one of the complications in flow control is these things all go hand in hand. You could certainly try different actuation schemes, but actuators themselves have interesting dynamics, which get embedded in this. So any reduced order modeling technique in a real experiment has to take into account the dynamics of your actuation system and the dynamics of your instrumentation, your measurement sensors, not just the fluid dynamics of the system. So if we change actuators, yeah, we could probably find other ones that would work quite well, but they would have different dynamics that would have to be identified in this.
Yeah, follow up. So the LQR you're applying after every update of the A matrix.
We can't do it that fast. They're both, I think I went back a few slides, but let me see. I think it's,
LQR is applied.
yeah, it's 250 hertz, so 250 times a second. So the LQR, basically what we do is we're solving this as fast as we can. And of course, that's a function of the number of inputs and outputs that we have. For this particular system, that's about 3 times the shear layer frequency. And that's 250 hertz. And so we just hold the cake matrix the same until we get a new update.
I have a question. So your basically your LQR controller is trying to push the pressure fluctuation.
Yes.
But your actual goal is to make the separation bubble shorter. So how do those two things relate to each other?
That's a good question. And I kind of glossed over that, but some of the earlier work on separation control showed that the two were sort of synonymous with themselves. And I think the physics of this, like I said, is that when the flow is separated, you have these shear layer structures, typically vortical structures, leaving like a footprint over the surface. And if the flow is then attached, you eliminate that disturbance. They're no longer present in this. Now, of course, if the flow is turbulent, you're always going to have a broadband spectrum. So the question is, will you get enough signal to noise in a system? We were looking at a laminar boundary layer. So really when it attaches the signal, if it's nice and clean, is very, very clean, and it does drive it to 0.
It's interesting because I can imagine that for a laminar boundary layer in particular, separation bubble, that you could have another solution with say 0 pressure fluctuations that are still has the separation bubble, but you've just killed
the oscillation.
Right.
Yeah, that's probably true in a wake, for example. Then I honestly haven't tried that myself, so I couldn't tell you, but I could envision cases where you're essentially killing oscillations, but there's still some steady recirculation. And then you'd be hosed in that case. You wouldn't be able to use this.
Right. I have one more, I guess, if there aren't other questions, but I'll give you first take any other questions in the audience. Okay, so in this case, you have this very small system, 13 by 13, and so you don't care that A is this dense matrix. Have you thought about how to apply this in cases where you have much bigger states and you don't actually want to form A? You want to compute them both in A?
I've thought about it. I don't have an answer to that. That's where guys like you come into play and tell me how to do this. That's a good question. And I think that may well actually be necessary when you go to more complicated flow, like a higher Reynolds number flow.
Final questions? If not, let's thank Lou again.